Today I talked about low vapor pressure volatile organic compounds. These are chemicals that are exempt from VOC regulations due to either their vapor pressure, their boiling point, or the number of carbons present. There was a lot of interest in identifying how rapidly these chemicals could partition into the atmosphere and whether individual species acted the same as mixtures or consumer products mixtures. We were also very interested in the ozone formation and SOA formation of these species using a large-scale environmental chamber reactor. So we designed an evaporation chamber system to look at the atmospheric flux or the evaporation rate of individual species. When we looked at mixtures, we used a selected ion flight tube mass spectrometer, which allowed us to measure directly the LVP-VOC we were looking at. As far as for ozone and SOA formation, we used a large-scale environmental chamber that we have at CSERT. We determined that the LVP-VOCs, even those that are exempt from VOC regulations, were able to evaporate given enough time. At least some of them were able to. Some of them were still low enough vapor pressure, they didn't do a whole lot. We saw a nice correlation that allowed us to estimate what that evaporation rate would be with molecular weight and vapor pressure. As far as the ozone formation, we were kind of excited to see that the current chemical mechanisms that we've been putting forward seem to explain the results inside of our chamber well. As far as the SOA formation goes, I was personally surprised to see that many of the LVP-VOCs that did not form as much aerosol as I initially predicted. I'd expected that many of them would form tremendous amounts of SOA simply because they were starting with a lower vapor pressure, but it turns out that only some of them were able to do so. Well, a few things come out of this for future work. One is it's very clear that the chemical structure is going to be very important in determining the amount of aerosol formation, not simply as vapor pressure that it starts with or the boiling point. So we're going to need to be able to identify which parts of the structure really lead to aerosol formation. Another key component that comes out of this is the actual availability of the individual LVP-VOC. Often when we look at a consumer product or some other mixture, we say we mixed it with all these different chemicals and we put in X% of this LVP-VOC. What's become very clear to us is that that percentage of LVP-VOC may not describe what's really available to get into the system and form ozone or SOA.